Hello students, I welcome you all to Engineers Academy. Do subscribe my channel if you haven't done it yet. Now we are going to solve this problem from Hibbeler dynamics, and the problem says that for a short time a rocket travels up and to the right at constant speed of 800 meters per second along the parabolic path y equals to 600 minus 35x squared. So this is the path of the rocket, right? So this red line represents that parabolic curve along which the rocket is moving, right? So it is said that determine the radial and transverse components of velocity of the rocket at the instant when theta is equal to 60 degree. So this problem is related to the cylindrical coordinates. So in the problem statement it said that we are required to find the radial and the transverse components of the velocity. So we have to find Vr and we have to find V theta using the cylindrical coordinates, and it is said that when theta is equal to 60 degrees, so when the radial axis is making 60 degrees with the horizontal, and it said that where theta is measured counterclockwise from the x-axis. Now, as we know that in case of the cylindrical coordinates, we have to define our reference point from where uh, the motion of a particle is observed, right? So let's say that somewhere here is, let's say if I extend this line, so let's say that somewhere here is my point O, and let's say that the radial axis is, let's say that the rocket is somewhere here. Let's say somewhere here is the rocket which is moving in the upward direction. In the problem statement it said that the rocket is moving, travels up and to the right. So it is traveling up and to the right. This is to the right, right? So let's say that somewhere here is the rocket, it is moving, right? So for that I have to define my radial axis, since it is the problem related to the cylindrical coordinates. So let's say that this is our radial axis, and this radial axis is making some angle theta, and that theta is measured in the counterclockwise direction. It is said that the theta is measured counterclockwise from the x-axis. So now let's say that this is my x-axis. If I choose that point O as my reference, so this is my positive x-axis, and my positive y-axis is going to be in the upward direction like this. So this is my positive y. So if the theta is increasing in the counterclockwise direction, so the theta axis will be in this direction. So let's define that theta axis. This is our theta axis. It's going to be in this direction, and this must be perpendicular to the radial axis. So this is the radial axis. We have to write that this is plus r and this is plus theta axis. This is plus r. Now we are given that the rocket is moving with a constant speed of 800 meters per second along the parabolic path, right? So that 800 meters per second velocity is tangent to this parabolic curve, right? This is that 800 meters per second velocity is tangent to this parabolic curve. So let's define our tangent at this particular point. So let's say that this is our tangent. This is our tangent line. I hope this is visible. If this is not visible, let's make it with some other color, right? So let's say that this is our tangent to the path at this particular instant, right? This is the tangent, right? This line is that tangent along which the 800 meters per second velocity is acting. Now let's make that velocity vector. So this is our velocity vector which is going to act along this line. So this is our velocity vector. This is velocity which is equal to 800, right? So now this theta is given, right? This theta is given, this theta is 60 degrees. So let me write that this theta is 60 degrees. Now what we need to do is that we need to find the, if we somehow find the angle of this v vector with the radial axis or with this theta axis, then we will be able to resolve this 800 meter per second velocity into its radial and transverse component. So for that, first of all, we have to find the angle of this tangential axis, or we can say that the angle of this tangent line to the positive x-axis. So let me draw the horizontal line here. Let's say this is my horizontal line, this is parallel to the x-axis. Let's say this is x dash. So first of all, we have to find the angle of this v vector with this x dash axis, and that will be, let's say, theta dash axis. So let's say that this is theta dash. Now we know that the slope of the tangent can be determined by taking the derivative of this path function, this y equals to, we know that y is equal to 600 minus 35x squared. So now if I take the derivative of this y as a function of x with respect to x, this is dy by dx, so this will give us minus 35 into 2 is 70x. So this is the slope of the tangent at any x value. So now we have to find the x value. If this angle is theta, then what is the x coordinate of the position of the rocket, right? So if the rocket is somewhere here, let's say if the rocket is somewhere here, then we have to find the x coordinate, right? We have to find this x coordinate of the position of the rocket. So this will be that x value. So once we know this x value, we will plug it in this equation, and then we will be able to find the slope of this tangent line. Now we are given that the angle is theta, that theta angle is given, so we can say that, let's say if I drop a perpendicular from this line, let's say from this particular point, so this is, so from here to here, this is that x. Let me remove this x-axis. This is x. Let's say this is the x, the horizontal distance of the rocket from the reference point, this reference O point, right? This is, so, and this will be y, right? Let me write that this is y. So this is y and this is x. So if we apply tan theta, if this is tan theta, let me write that tan theta is perpendicular. So this perpendicular is y divided by x. This is x. So now, and we know that the angle is 60, right? So we can say that tan 60 is equal to y divided by x. Or we can say that y is equal to tan 60x, right? Tan 60 into x, right? So tan 60, we can find tan 60. This is tan 60, so it is 1.732. So y is equal to 1.732x. So now this is the y as a function of x, but when O is taken as the reference. So now if I plug in this value, if I plug in this y as a function of x in this equation, so that this equation will give us that x value where the rocket is located when the radial axis is making 60-degree angle with the horizontal, right? So now if I put this in this equation, so this will be equal to 1.732, since y is 1.732x, equals to 600 minus 35x squared. Remember that this equation and this equation, they are different equation, right? For this equation, the origin is somewhere else. For this equation, the origin is somewhere here, right? And this equation tells us the path of the rocket along which it is moving. But this equation, if we plug in this equation, that will give us that x value, that is the horizontal distance of the rocket from point O. So now if we rearrange this equation, this is, you can say that this is minus 35x square, and now if I bring this to this side of equation, so this will become negative as well. So this is minus 1.732x plus 600, and this is equal to 0. So now let's find the roots of this quadratic equation, right? So we have to find the roots. So the coefficient of x square is minus 35, then minus 1.732, and this is 600. So now we will get two values of x. X is equal to, the x coordinate is equal to 4.12 approximately, and then we have one another value that is minus 4.17 meters. So now if we observe the path function of the rocket, so the rocket is somewhere here. If the rocket is moving towards the right and it is rising up, so it must be on the left side of this origin, right, for the path function. So this must be the negative value, right? From this side, this must be the negative value. So we have to accept this negative answer, this negative root. So now once we know this x value, the rocket will be at a distance of minus 4.717 meters when this radial axis is making some angle theta, that is 60 degrees, right? So this means that 4.17 will be, if this is minus 5, so minus 4.17 will be somewhere here. So this means that rocket is somewhere here when this radial axis is making 60 degrees. So we have to accept this negative value. So now once we know this x coordinate of the rocket, from this origin we will plug it in this equation, and we will be able to find the slope of the tangent to the path, right? So we can say that dy by dx is minus 70 into minus 4.17. So this gives us minus 70 into minus 4.17. So this will become positive. So this gives us minus plus 291.9. And we know that dy by dx, the slope of a straight line, is always represented by tan theta. So we can say that this dy by dx is also equal to tan theta. But the tangent, we have assumed that the tangent line is making angle theta dash with the x-axis. So we have to say that this is theta dash, right? So now we can find this theta dash. We can say that theta dash is tan inverse 291.9. So tan inverse 291.9, this gives us 89.80. So theta dash is 89.80 degrees, and this is positive value. So the positive sign tells us that this angle is measured in the counterclockwise direction from the horizontal, that is from this x dash axis. So this is that angle theta dash which this velocity is making with the x dash axis. If this velocity is acting along the tangent and the tangent is making this degree, this much angle, then the velocity is also making this much angle with the x dash axis. So now we know that this velocity is 800 meter per second, and it is making 89.80 degree angle with the horizontal. And we know that this radial axis is, making angle 60. So if it is making angle 60 here, it is also making angle 60. So let's say that this is that angle theta. And we are interested to find the angle of this velocity with the radial axis. So what will be the angle of this velocity with the radial axis? Let's say that this angle is phi. So now we can say that phi is equal to theta dash minus theta, and theta dash is 89.80 and theta is 60. So phi will be equals to 29.80. So now, if once we know the angle of the velocity with the radial axis, we can resolve it into its components. So it will have one component along the radial axis, and it will have one component along the theta axis. This one will be VR, this one will be V theta. And since the angle is made with the radial axis, so VR will be the cos component. So we can say that VR is equal to V cos of phi, and V is given, this is 800 cos of phi is known, 29.80. So this is 800 cos of 29.80. This gives us 694. So the radial component of the velocity is 694.21 meter per second. And similarly, V theta will be the sine component, that will be 800 sine of phi. So this is 800 sine of 29.80. So 800 sine of 29.80, this gives us the transverse components of the velocity equal to 397.58 meter per second. So this is the radial component of the velocity, and this is the transverse component of the velocity which was required. So this problem is a little bit tricky. I hope you people would have understood this problem. Kindly subscribe Engineers Academy if it helps in your learning. It will help me a lot.